Welcome everyone to our Critical Issues webinar series. My name is Leila Gonzalez and I'll be moderating today's Critical Issues webinar, Induced Seismicity in the Mid-Continent. We would like to acknowledge the co-sponsors of today's webinar, and that would be the Association of American State Geologists, and I'd like to thank them for getting the word out about this webinar as well. Now our schedule today, we will be having Bill Ellsworth from the U.S. Geological Survey, who will be giving us an overview of induced seismicity. Then we'll be hearing from Austin Holland from the Oklahoma Geological Survey, who will talk about the potential for induced seismicity and current mitigation efforts within Oklahoma. And then we'll hear from Rex Buchanan from the Kansas Geological Survey, who will discuss recent seismic activity in Kansas, events and responses. The presentations will be followed by a panel discussion where questions from the participants will be addressed by the speakers. And again, you can ask questions by typing them into the question box on your webinar panel at any time throughout the webinar, and we'll go ahead and field those during that Q&A session at the end. I'm going to go ahead and turn the slides over to Bill, and we'll kick off our presentation.
Thank you very much. Well, good morning, everyone. I'm going to be talking about the science of induced earthquakes to give you a background about our understanding, where it comes from, and how we are using that understanding to evaluate the hazard that they pose, and to finish with a brief overview of where USGS research is going. And I would remind everyone that the U.S. Geological Survey is a research agency. We're not a regulator, but we hope that our science is able to inform those who are involved in both the policy decisions and operational decisions. So let's get started. So what is an earthquake? We should start there. The earthquake is the sudden shaking of the ground caused by slip on a fault. And if we look at my little cartoon over here, the fault is something which is usually deep underground, and it is the waves generated by the rapid movement of the fault that we feel at the surface. The movement of the fault is illustrated here by the arrows, and in general, the larger the area of the fault, thinking about the blocks being larger, the larger the earthquake will be. During an earthquake, it releases long-stored elastic energy, and that is what causes the fault to slip suddenly. And an earthquake will begin when those stresses that want to drive the fault forward exceed the frictional strength of the fault. So the stresses here represented by the red arrows on opposite sides of the slipping fault, they will be resisted by the clamping stresses, the arrows that I've just brought up. So it's the balance between the forces that are trying to accelerate the block to cause the earthquake, cause the fault to slip, against those that want to keep it locked. That's the balance that we're concerned about. And of course, earthquakes occur in all types of settings all around the world, not only on the plate boundaries, the areas that are illustrated here by the many dots, but also in the interior of the continents, such as here in the United States. Well, human activity can induce earthquakes in several ways. Both of these are well understood. The one on the left shows in cartoon form the direct fluid pressure effect. This is where by raising the pressure underground we can reduce that clamping stress on the fault, allowing the fault to come to failure. The other way that an earthquake can be induced is by changing the shear stresses acting on the fault, and that can be done in a number of ways, such, for example, if we pull mass or volume out of the ground, it can be changing the stresses at greater distance, and that could be loading a fault to failure. This mechanism is one that has been well understood for a long time, this solid stress effect, and here's just an example from several papers in the literature. A 1986 paper studying some oil fields in South Texas, and then a 1995 paper studying more earthquakes in the same oil field. And in both cases, it was quite clear that these earthquakes were being induced by the withdrawal of fluids. In fact, some of the recent earthquakes in this area have in fact been in the same fields, and we understand that they are being produced by the same mechanism. Now, the other mechanism that is important is the pore pressure effect, and we think this is probably the most important effect in terms of the rise of seismicity that we've seen across the mid-continent. So again, when we inject fluid underground, the process of injecting fluid is going to be displacing water that's already occupying the pore spaces, and that will cause pore pressure to increase, often at great distance from the injection point. And if that increase in pore pressure reaches an ancient fault, it can decrease the normal stress, shown here by these arrows, that weakens the friction and allows the fault to come to failure. Mathematically, we express that as the critical shear stress, shown by these arrows, is equal to the coefficient of friction times the effective normal stress. The normal clamping stress that's in the earth minus the pore pressure. So by raising the pore pressure, we can reduce the frictional strength, allowing the fault to fail. Faults are found virtually everywhere in the earth, and they occur on a wide variety of scales and in every geologic setting. So it's very difficult to directly avoid faults, but again, the size of the fault will determine the size of the earthquake. So if we can avoid large faults, we can reduce the potential for inducing a large earthquake. We also know that everywhere in the earth, the stresses are high. They're near the failure stress almost everywhere. So it takes only a small change in pore pressure in many instances to bring a fault to failure. So some examples of this mechanism can be found in recent studies. So for example, in western Colorado, right on the Utah border, is a location where the U.S. Bureau of Reclamation is sequestering salt water so that it doesn't enter the Colorado River system. They do this by injecting it into a deep well. That injection process generates many earthquakes. So this is a clear example of how injection is inducing earthquakes. In this case, they're an unintended but necessary byproduct of the process of sequestering the salt from the Colorado River. Another example that many of you will know about is the earthquake that occurred on New Year's Eve in Youngstown, Ohio in 2011. This is an earthquake that was induced by disposal of wastewater, primarily fracking fluids that had been trucked in from Pennsylvania into a deep well. And it's quite clear that this is these earthquakes were ones that were induced by injection into this well. Another example comes from central Arkansas, the area around Guy and Greenbrier. This is an area, again, where disposal wells were disposing of hydroflac waste fluids, and they allowed an ancient fault to become reactivated, generating some earthquakes up to about magnitude 4.7. And finally, in another example from the literature is the earthquakes that were occurring on the Dallas-Fort Worth airport property. They could be traced directly to, again, a wastewater well that was located on the airport property. So there are now many studies in the scientific literature that document this process. This is actually not a new idea. It's something we've known about for a long time. Here are the covers of a couple of books, APG Monograph 1968. This is the American Association of Petroleum Geologists. This was something that was looked at very seriously in the early days of wastewater disposal, and they realized that tremors being the result of the release of stress when injection pressures produced by injection of fluids overcome the friction on opposing rock surfaces. So the same mechanism that I was discussing. 1976 paper by them was looking at the Denver earthquakes, and this is really the important discovery location for this process. So let's take a little bit deeper look at what went on in Denver in the 1960s. So east of Denver, near the current Denver airport, was the Rocky Mountain Arsenal. This was a chemical weapons plant that was in operation during the Cold War. They had some very nasty stuff that they needed to dispose of, and they chose to do this by injection into a deep well. Injection began in 1962 with the volumes of injection shown here by month in the top graph, and then below is the earthquakes that were felt in the Denver area. And for many years, these were quite mysterious. Why were there earthquakes in Denver? And it was eventually tracked down that they were related to the wells. And I think you can see that there's a clear correlation here between the earthquake activity and how much pumping occurs. Now, what's quite interesting at Denver is that the pumping ended in early 1966, but the earthquakes continued for more than a decade, with the largest earthquakes occurring in 1967. And in fact, many of the earthquakes occurred well away from the injection point, up to about 10 kilometers away, extending well into the crystalline basement rocks. The things that we learned at Denver were that first, the earthquakes were induced by injection of the chemical waste in this deep well. The fault was releasing long-stored tectonic stress on really an ancient fault, and earthquakes occurring quite far from the injection point. And the largest earthquake with a modern magnitude, we would say 4.8, occurred 1 year after injection stopped. And earthquakes continued actually into the early 1980s. Well, this is an important correlation, but is it causation? This is something that U.S. Geological Survey actually tested in the late 1960s with the cooperation of an oil company in western Colorado. They gave the USGS permission to operate some of the wells in the corner of the field, and that by varying the pressure in these injection wells, it was possible to produce many earthquakes or by reducing the pressure to cause the earthquakes to stop. In the laboratory, we measured the coefficient of friction, we measured the stresses, and we knew the pore pressure. So this was an actual prediction, a prospective test of the theory, and it showed that indeed the earthquakes were being induced by this fluid pressure effect. Quite importantly, we found that the earthquake stopped largely stopped within a day of backflow, in other words, reducing the pressure. So there's a direct cause and effect here that we can use to our advantage. So I want to step back now and take a look at the earthquake hazard issue. The map shown in the upper right corner of the diagram here is the current version of the National Seismic Hazard Map. The colors here represent levels of shaking that are unlikely to be exceeded even in a 50-year period. The red areas are obviously areas of the greatest concern. Of course, the West Coast, where we have the active tectonics. You'll notice here the New Madrid region, South Carolina, around Charleston. These are all areas where there have been historic earthquakes and good evidence that earthquakes have happened multiple times in the past. Over most of the mid-continent, things are relatively quiet. You can see a little bit of a hot area in Oklahoma. That's due to some earthquakes that we know about, both in historic time but also prehistoric earthquakes. Now, the way we go about making these maps is we gather information about where earthquakes will occur or are likely to occur, gather information about how frequently they will occur and what their magnitudes are, combine that with measures of how strong an earthquake will shake the ground to come up with the values that are shown on this map. Now, one of the key components of this map is the assumption that earthquake rates will be the same as they were in the past. And so, for example, if we look in this mid-continent area and just simply count the number of earthquakes with magnitudes greater than 3 since 1970 through 2004, we find that they're marching forward at a fairly steady rate. So projecting that line into the future seems like a safe thing to do. That's not how it worked out, however. So instead we have this kind of hockey stick where the earthquake activity has accelerated in recent years, and in fact has accelerated even more off the end of this diagram. So a higher rate of earthquakes implies a higher hazard, but how much higher? That's the question we'd like to answer. And how long will the higher hazard last? Well, the U.S. Geological Survey and the Oklahoma Geological Survey have in particular been drawing attention to the unprecedented earthquake activity in Oklahoma. In late 2013, we released a factual statement that describes the rise in earthquake activity where there were only 1 to 2 of these magnitude 3 or larger earthquakes in Oklahoma per year on average, and that number it began to increase in 2009, increasing very greatly in 2014. In fact, leading to last year more earthquakes of this size in Oklahoma than in California. Of course, it's important to note that in California we had a magnitude 6 earthquake, whereas the largest earthquake in Oklahoma last year was less than magnitude 5. Well, to understand these problems, the USGS and the Oklahoma Geological Survey felt we needed to gather all the stakeholders. We held a meeting in Midwest City in November last year that brought together over 150 participants from industry, state and federal geological surveys, academia, regulatory agencies, state insurance and transportation agencies, and so on, to grapple with this problem. And one of the strong recommendations from, really a consensus recommendation of this workshop, was that they would like to see the USGS develop an annual seismic hazard map for these areas in which earthquake activity has increased recently. So that's the process that we're working on now. We're not quite there yet, but we do have a report that will be released soon that is a summary of the workshop, and it will describe some of the issues that will be needed, that we need to solve to be able to build a hazard map going forward. I can give you just a very brief look about what a preliminary hazard map would look like. This is just one example. It's certainly not a final product, but it shows the shaking levels that are unlikely to be exceeded, only 1 chance in 100 that they will be larger than these values over the next year. And you can see, for example, that in the New Madrid seismic zone there is a small shaking hazard at this probability level, and a somewhat higher level in some of the hot spots in Oklahoma that we see lit up almost on a daily basis. So moving forward, for the USGS, our goal, as I mentioned, is in the short term to develop a 1-year hazard map that will incorporate both natural and man-made earthquakes. We're also working on communication of the hazard to the public, elected officials, regulators, and industry. We're going to continue to collect data to improve the accuracy of these hazard models, including the nature of the earthquakes and the ground shaking they produce, and importantly, continuing the research to develop a process-based understanding of these induced earthquakes, because we think that will really give us a much better heads up about how to proceed and really to help those who need to regulate this activity in a way that will be responsible going forward. So with that, I'll thank you and turn things back over to the moderator.
Thanks, Bill. I'm going to go ahead and switch the slides over to Austin.
Like Bill, I'd like to just say that the Oklahoma Geological Survey is not a regulator. We are a state agency for research and public service. I'm going to show a fair number of slides that talk about the regulations that are occurring as a sort of an informational piece as to what's going on in Oklahoma, and hopefully I represent the Oklahoma Corporation Commission well, so they've provided a significant input on this as well. We have funding to look at these issues further from RIPC, and then we have many different partners throughout the country and the state as well. So Bill talked about the increase in the number of magnitude 3 or greater earthquakes within Oklahoma. One of the questions or things we still have to deal with is how do we know that this is so different from that of the past? And so one way to look at this is to look at the number of magnitude 4 or greater earthquakes that have occurred in Oklahoma. We have a record of these earthquakes going back to 1882 based off of historical accounts of people feeling earthquakes that are recorded in journals and newspapers and that sort of thing. And so we used to, in Oklahoma, when seismicity rates were sort of at a steady rate, we averaged about 1 magnitude 4 earthquake every 10 years. And just to really put this in perspective, things started to pick up in 2009 through 2013. We averaged 3 earthquakes each year. And last year alone, in 2014, we had more than 10 magnitude 4 or greater earthquakes. We had 15. So a good way to say this is that we experienced more than 100 years of normal Oklahoma seismicity in 1 year. So the seismicity rates are quite dramatic. And needless to say, the Oklahoma Geological Survey Seismic Monitoring Program is really working hard to keep up with those. And as Bill said, the number of earthquakes within Oklahoma of magnitude 3 or greater exceeded those in California. So this is a real effort, and we certainly are doing our best to document the seismicity within Oklahoma. So having said that, we see the primary concentration of earthquakes occurring within central and north central Oklahoma. This area represents about 15% of the aerial coverage of Oklahoma. So it's a very large distribution throughout Oklahoma. This area also captures a significant number of wastewater disposal wells and wastewater disposal volume that I'll get into in a little bit. So just to show that we're truly capturing the greatest amount of increase in that portion of central and north central Oklahoma, I've shown the cumulative volume or cumulative number of earthquakes in the gray area and the blue area, and you can see that the areas of central and north central Oklahoma have the greatest rate of earthquakes, and we do see some rate increase in other portions of Oklahoma, although much less than in the central and north central part of the state. So one of the things we're working on at the Oklahoma Geological Survey is understanding the wastewater disposal within the state. So Bill talked about a number of cases where we had recent disposal wells that were disposing of hydraulic fracturing waste fluid and triggering earthquakes in the cases of Ohio and Arkansas. Most of the water that's disposed of within Oklahoma actually comes from the production of oil and gas. This is naturally occurring saltwater brines that are in the formations with the oil and gas. And as part of producing the oil and gas, they remove this water from the subsurface, and this water is not of drinkable water or of water quality sufficient for surface discharge, and so it's re-injected into the ground. The primary formation in which this water is injected, as can be seen in the bottom panel, bottom left-hand panel, is the Arbuckle Formation. This formation can take large amounts of volume with little or no pressure. This formation is the deepest sedimentary formation of any significance, and it's broadly available for disposal throughout most of Oklahoma. It overlies the crystalline basement, that is the metamorphic and granitic rocks that underlie all the sedimentary rocks in which the oil and gas reside. So this is the primary target of our concerns within the state, is the injection that's occurring within the Arbuckle as well as the basement, as I'll get into a little bit further. But as we can see, the largest injection volumes and greatest concentrations of wells occur within central and north central Oklahoma. So we have this broad correlation in space, and the earthquakes appear to be lagging the initiation of large injection volumes within these regions. We do see other areas with very large injection volumes that don't have as much of a response to the injection with earthquakes, and that remains to be examined why some areas may be more prone to triggered seismicity from fluid injection than others. So one of the efforts we're undertaking here in Oklahoma is to create a database of faults within the state. As Bill mentioned, the size of fault dramatically affects the size of earthquake we might expect. And so we've compiled this fault database from both industry contributions and published literature. I have a student daily adding faults from published literature into this database, and we certainly are hopeful that we'll get more industry contributions, but we've gotten a very large number of industry contributions to date. We are working on documenting this effort so that then we can make this a publicly available database for all stakeholders doing either research or trying to understand what's occurring within Oklahoma. But this is a good first step towards understanding where we might want to examine injection activities further, as we'll see here in a minute. So in Oklahoma, we've developed sort of this interagency cooperation as the earthquakes began to pick up in 2010. I began to interact with the Oklahoma Corporation Commission, who's the regulator of these disposal wells within the state of Oklahoma, on a weekly and nearly daily basis. And so the primary resource we have is data, and we've been trying to compile data and condense this data and make it usable for the regulators within the state. We've been working with industry partners and other research partners to improve our understanding of what's occurring, and as well we're also gaining then more information about injection and operational data from the oil and gas wells that the Oklahoma Corporation Commission is making publicly available that can support additional studies to move forward. So the Oklahoma Corporation Commission UIC program was created as part of the 1974 Safe Drinking Water Act. So all the regulations surrounding disposal wells are designed to protect sources of drinking water. And so the regulations were designed to ensure that surface and underground drinking water is protected by these oil and gas operations. The Corporation Commission received primacy in 1981. There are two types of Class II disposal wells. There's what the Oklahoma Corporation refers to as 2D wells, or saltwater disposal wells, and then there are the 2R wells, or the enhanced recovery wells. So EOR wells re-inject produced water back into the same producing formation to help extract remaining oil within the formation. There are about 4,000 saltwater disposal wells and about 7,000 enhanced oil recovery wells operating within the state of Oklahoma. So the disposal wells take wastewater from the oil and gas industry and inject it into the subsurface. The water is not generally what we think of as water. It has very high salinities, much greater than seawater, and there are often other hydrocarbon and chemical constituents that don't get removed before the water is re-injected into the subsurface, and that's primarily where the regulations surrounding the protection of drinking water lie. This wastewater comes from two primary sources. The largest and for the state of Oklahoma is naturally occurring water that is removed with the oil and gas. This is called produced water. And the smaller amount of volume is hydraulic fracturing or flowback water. It's a relatively small amount of the total amount of volume injected within the state of Oklahoma. Of the 4,626 disposal wells within Oklahoma, almost 1,000 of these wells are permitted to dispose of water in the Arbuckle Formation, which I mentioned is the deepest formation of disposal within the state of Oklahoma. So last year, or I guess the year before, the OCC implemented a traffic light protocol. These are modified permits. And so as an operator comes into an area and wants to inject fluid within an area and is getting a permit for a disposal well, there is now a check whether the location of the proposed well is within any close proximity to optimally oriented faults or significantly large faults, or within some distance of seismic clusters, or in an area of interest, which I'll get into further. And if they are, the operators ask for a technical meeting, and the operator is asked to demonstrate the level of risk of induced seismicity and provide more technical data. The application is required to go to hearing, and the staff take a neutral position on whether the well is a seismic risk for triggering earthquakes. So last year, the Corporation Commission went with areas of interest. That was a 6-mile or 10-kilometer buffer around magnitude 4 earthquakes. And so here we can see what that area of interest map looked like. They took all magnitude 4 or greater earthquakes from 2013, and this shows through February of 2015. And you can see that it highlights a number of areas where we've seen increased seismicity within the state of Oklahoma. But it was realized that this maybe didn't capture all the areas of interest. And so they've now redefined the areas of interest to include seismic clusters. And a cluster, according to the Corporation Commission, is defined as an area consisting of at least 2 events with epicenters within a quarter mile of each other, with at least one event with a magnitude 3 or greater. And the area of interest is then a 10-kilometer or 6-mile buffer from the cluster center. And so the new areas of interest are shown with the red outlines in the hashed color area, and the green circles show the previous magnitude 4 areas of interest that were defined before this aerial definition that was created by the Corporation Commission. So this captures most of that area in which we saw the significant increase in seismicity within the state over the last few years. So this shows for the whole state, the primary concentration, largest areas of interest, again, are in central and north central Oklahoma. Along with this new definition of area of interest came also new actions for Arbuckle Disposal wells. All Arbuckle Disposal wells must provide the following. Operators must provide information to the Oklahoma Corporation Commission Oil and Gas Conservation Division that the Arbuckle Disposal wells within the area of interest are not in contact or communication with the crystal and basement rock. Wells found not to be in contact or communication with crystal and basement will be allowed to resume normal operations. Wells found to be in contact or in communication with crystal and basement must plug back. And that's according to then plans developed with the Corporation Commission. And so this directive was sent out March 18th. Operators have 7 days to begin reporting, and operators have until April 18th to provide their information to the Oil and Gas Division. Operators who do not provide this information or do not have an approved plugging schedule will be required to reduce their disposal volumes by 50% until they satisfy the directive. So the rates of seismicity have increased dramatically, and as such, so is the seismic hazard within Oklahoma. So earthquake preparedness is being communicated to the public. That's something that the public can do to protect themselves, their families, and those in their community, is to understand how to prepare and what to do during an earthquake. The OGS and the OCC continue to provide data products to stakeholders and identifying new data sources. Multi-agency cooperation and data exchange and sharing are critical in addressing issues with informed science. Developing a greater understanding of the physical processes in Oklahoma will help to inform future mitigation strategies. So that's really where our research is focused. And thank you for your time.
Thanks, Austin. And I'm going to go ahead and switch the slides over to Rex next.
Okay, thank you. I just want to start by saying thanks to AGI for arranging this webinar today. I think it's a timely topic and one that's certainly of interest to folks in our part of the world, and I think a lesson in a variety of issues related to science and public regulation and public communication. We'll go to the next slide. Just as Austin said, the Kansas Geological Survey is part of the we're a division of the University of Kansas. We have research and service responsibility. We don't have any regulatory responsibility. When it comes to this issue, we've worked closely with the Kansas Corporation Commission. They're the agency of regulatory responsibility for the state of Kansas, primarily for oil and gas, and so we've worked closely with them the way that the OGS has with the OCC. This is a map showing historic earthquake activity in Kansas. The legend down at the bottom is modified Mercalli, obviously, and you can see that Kansas, for the most part, is a relatively aseismic state. There's not a lot going on, and where it is, it's mostly along the Humboldt Fault Zone or the Nemaha Ridge. They're in sort of east-central Kansas. It goes north and south across the east end of the state. The next slide. We operated a seismic network with funding from the Nuclear Regulatory Commission and the Army Corps of Engineers from 1977 to 1989, and these are the results of that activity. And again, you can see that we recorded a fair number of earthquakes in Kansas, but nothing like what we'll talk about here in a second. I would point out a couple things. One, we did see a lot of activity, as you would expect, along that Humboldt Fault Zone, and we saw some in this area of north central Kansas that today I think we might very well likely attribute to induced seismicity related to water flooding activities in that part of the world. I'll call your attention especially to this part of the state down here along south central Kansas, because that's really the area that we'll be talking about from now on. And we'll go to the next slide, which will show earthquake activity, and really we'll focus for almost the entire rest of the time here on really two counties in south central Kansas. We're right down along the Kansas-Oklahoma border. These are Harper counties to the west and Sumner County to the east. When Oklahoma began to see activity in 2011, we really didn't see anything until 2013. In September of 2013, we began to see these events mostly in this area of, like I said, in Harper County to the west, and then in this area, sort of southeastern corner of the county. This is really the largest event that we saw. That was in December of 2013, a 4.3 right on the edge of Sumner County. These events got our governor's attention, and probably what I'll talk about will be a little bit more of the public component of what we've been dealing with, since Bill and Austin covered a lot of what the mechanisms and some of the other issues associated with this issue. Our governor brought us together to talk about these events in the fall of 2013. We'll go to the next slide. Then in 2014, we began to see even more events. This slide is a little different scale. Just point out, here's Harper County, one of the counties I just talked to you about. Sumner County is here. These events correspond, the size of the dots corresponds with the magnitude of the earthquakes. I'll just call your attention, the largest city in Kansas is Wichita, which is less than 30 miles from where we're seeing a lot of this activity. Also, we had a couple of outliers in this process, one earthquake over here and another one up here that basically at this point are not only quite a ways from where we were seeing that other activity, but also quite a ways from any large volume disposal wells. At this point, I think the consensus is that those might very well be natural events. Next slide. This is a close-up of that activity in Harper and Sumner County. So again, we've shifted scales and we're back in Sumner County with these events and Harper County with these events. This is 2014. We'll go to the next slide. The largest of those events was a 4.9 event that occurred in, then actually, if you could back up one slide, the largest of these events is sort of covered up by some other dots, but it's right here. It was a 4.9 event in mid-November of 2014. The closest town is the town of Milan. This is a relatively rural area in the state. There was some small damage. Go back, then go to the next slide. This is what probably is some damage. These are older buildings, brick buildings in that town. This is probably earthquake damage related to that event. This is maybe earthquake damage on an old post office there. We'll go to the next slide, which shows a schoolhouse and maybe some damage both here and here, but obviously this is minor amount of damage. You might be saying, well, what's a big deal on a 4.9 earthquake that doesn't cause any more damage than this? I guess my answer would be, in a part of the state that is not accustomed to high levels of activity, when you begin to see these kinds of events, you begin to worry about other kinds of structures like schools and courthouses that we've got there that certainly were not built to withstand some of the level of earthquakes that folks in Oklahoma have seen and what we might be concerned about in the future. So even minor amounts of damage will get your attention. Next slide. This is 2015 earthquakes, and you can see the beat goes on here. Sumner County here, Harper County here, and again, things haven't slacked off at all. Next slide. This is a graph showing both magnitude, a graph over time beginning in January of 13, and really you can see when that activity starts in September of 13, and then really almost sort of peaks out in terms of magnitude 2 and larger earthquakes, and then you can see a few 4 and larger earthquakes in November of 14, and then you can see the numbers continue in 15. Basically in January and February of 2014, our governor called the agencies involved with this issue together. Next slide, Lila, and began to talk about response. This correlates pretty closely in time, and Austin touched on this, with a Mississippian oil play that was moving into the state from Oklahoma and really started down here in Harper and Sumner counties. It sort of died out with both, it wasn't as productive as people thought it had been, and then with lower prices, so it's really still focused here. We've got a lot of horizontal wells and a lot of big volume disposal wells. Next slide, down in those two counties. And there are some of the brine disposal trends. Both the brine disposal trends on the right in terms of total volumes that you see, those are just for those two counties that change over time. These are numbers that come from our Corporation Commission, a well count on the left, and you can see the increase in just those two counties. Next slide. So with that, the Kansas response, the governor created a task force on induced seismicity. The three agencies are the Geological Survey, Kansas Corporation Commission, and Kansas Department of Health and Environment. Health and Environment is on here because they regulate Class 1 disposal wells. Austin talked about Class 2 disposal wells and defined those pretty accurately. KCC regulates those in Kansas. KDHE regulates Class 1 wells, which tend to be more hazardous waste types wells. Lots fewer of those in the state, but they are of concern with this issue. So those three agencies formed the task force. We had a number of meetings. Public meetings, developed a plan, got comments, revised the plan. The two primary things that came out of that plan, one was enhanced monitoring. I'll talk about that in a minute. The other was a seismic action score that consists of trying to both tease apart natural from man-made events and also guide the response. And that scoring is based on not just the magnitude of the earthquake, but also the clustering effect that Austin talked about before, and whether there were habitable dwellings anywhere close. Try to take all those into account. And then if we exceeded a score of a certain threshold, it would require the KCC to collect information and KDHE to collect information on disposal wells within 3 miles of the epicenters of those events. Just to point out something, we've got, and Austin touched on this, we've gotten an awful lot of help from a lot of people in this process. I particularly want to point out help from the USGS, and I'll talk about them more in a second. Almost all of those previous maps that I showed you showing those magnitudes and locations were maps based on data from the USGS and the Oklahoma survey. When this started, we had no stations here in Kansas operated by the state. There were 2 operated by the USGS. We were really under-instrumented. So we were real reliant on the USGS for NEIC, National Earthquake Information Center, for data, and from the Oklahoma survey. The network that I'm getting ready to describe included instrumentation that we got from the University of Missouri, so we've had a lot of help. We've also put a focus, as Austin touched on public information, trying to communicate with the public and listen to the public about this issue. Also done a lot of work in terms of legislative interaction and testified regularly about this. That's been one of the challenges. Public communication has been a challenge in this process. I also want to point out we're working, Austin and the folks at the USGS both, and a variety of folks are working with the Interstate Oil and Gas Compact Commission and the Groundwater Protection Council on an induced seismicity task force that's dealing with this issue as well, and we've gotten help from those folks. The next slide. That seismic action plan is up on the web. I'll give the URL for that here at the end. Next slide. This is that temporary network. The 2 counties I mentioned, Sumner and Harper counties, those they show up as orange triangles, are a temporary network that the USGS, Justin Rubenstein and the folks at the USGS installed last April when we began to see an uptick in events. The other dots, the green and the blue ones should now be green. Those are stations that the Kansas survey, temporary stations the Kansas survey has installed to try and get maybe a little more broadly outside of where we're seeing the primary focus, and maybe also get into some of these counties where we haven't seen much activity yet to try and develop background data before we do see activity. Next slide. This was a response from the KCC. This is based on an order that just got released about 2.5 weeks ago. Again, the counties that we're talking about, this is Harper County here, this is Sumner County over here. They ask us to identify areas of concern, so those linear features are both where epicenters have clustered up. They're also based on some gravity and magnetic subsurface data. The KCC then drew 3-mile ellipses around there to identify zones of concern. They identified 5 of those in the 2 counties, and within those 5 areas have ordered the companies to do sort of a series of staged cutbacks over the first, beginning with the order. They will cut back all the disposal wells within those ellipses to 16,000 barrels. Within another 55 days, they have to go back to 12,000 barrels, and then at day 100, they have to be reduced to 8,000 barrels per day of disposal within those areas. And then at the end of 100 more days, we'll monitor, obviously, to see what we get in the way of events at the end of 100 more days or 180 days from the time of the order. We'll see what the response has been in terms of seismic activity and make an appropriate decision about, the KCC will make an appropriate decision about how to alter that order at that point. Next slide. Obviously, I said communication has been an important part of this. This is a circular that we've developed to communicate with the public on this issue. Next slide. And this is my last slide. The Kansas, it has the URL for the Kansas Seismic Action Plan. That order that I just showed you the map from the KCC is the second thing. We've put up a number of resources on induced seismicity on our website, that third URL. The fourth one is a statement on induced seismicity that was developed by the Association of American State Geologists, is that URL. One other thing I might point out that I should have put on here that I didn't, the National Research Council, National Academy of Sciences in 2012 did an excellent report on induced seismicity, variety of resources that go along with that, including a nice video that has been highly useful for public communication. So those are some of the resources that are now available that we've referred people to. And with that, I'm done, and appreciate your attention, and again, appreciate AGI's work on this webinar.
Thanks, Rex. We're going to go ahead and start fielding questions from the audience at this point. The first question we have is, can you talk about the distinction between hydraulic fracturing, wastewater disposal, as they relate to induced seismicity?
This is Bill Ellsworth. I could take that question. That's really a good one, and there's a lot of confusion regarding this issue. So let me see if I can help clarify this. Hydraulic fracturing is a process that is used to improve the flow of either oil or gas to the production well, and it is a brief pressurization of the well, which causes many tiny earthquakes we call micro-earthquakes, then introduce new fractures into the rock that allow the oil or the gas to flow to the well. It's a process which has been used maybe more than 1 million times in the United States, and as far as I know, no earthquakes as large as magnitude 4 have ever been associated with the process. So while it has some hazard associated with it, we think it's very small. It's also a very brief process. It may last for a day or two at a particular well, and after the operation, the hazard goes away. Wastewater disposal, on the other hand, as both Rex and Austin explained, is something that can go over periods of many years and often involves very, very large volumes of fluid going underground. Although the pressure rise during in the disposal process may not be very large, it can be enough to induce favorably oriented faults to slip if the stresses are high enough. And in these areas that both Rex and Austin described, we've seen that the empirical evidence suggests that these pressure fronts actually move quite a distance away from the wells, such as we know occurred both at the Denver Rocky Mountain situation and at the Rangeley experiment.
Great, thanks, Bill. And we've got a couple other questions. One is, how deep are the faults that are causing earthquakes?
I can handle that for Oklahoma. So, and actually this is true in a lot of these cases of triggered seismicity. Most of the faults that are slipping and having earthquakes are within the crystalline basement and generally below the injection zone that's the water is being injected into.
Great. There's another follow-on actually to that, also asking about, can the injection of fluid ever create a new fault, or is induced seismicity always associated with a dormant ancient fault?
Well, certainly in the case of hydraulic fracturing, a new fault can be formed if the pressures are high enough. We of course don't know where all of the ancient faults are, but in cases where we have, through industry cooperation, been able to look at seismic images, it's been possible in many of these cases to identify the place where the earthquakes were occurring with a pre-existing fault. So our understanding is that the majority of these induced earthquakes are in fact occurring on ancient faults. And it's really only those ancient faults that are well oriented in today's stress field. So this is why the work that Austin was describing is so important, to not only understand where the faults may be located, but also what the orientation of the stresses are. Because some faults will be capable of slipping and others will not. And it's really important to identify those that are going to be most hazardous because they're well oriented.
This is Rex, and yeah, just to sort of bring, again, our perspective on this, I would agree with everything everybody said. And I think everything that we've seen, these have all been basement faults, pre-existing faults. But we struggle to know the location. There are an awful lot of faults out there that we don't know the locations of, and we're working sort of the same way the folks in Oklahoma are to identify those. And I would also, just to add back to the first question, I don't think that we've seen any felt earthquakes in Kansas that we can associate with hydraulic fracturing at this point.
If I could add one other thing to what Rex said, he made a very important point here, which is that we don't know where many of these faults are, and the way we'll find out about them is that they'll begin to produce earthquakes. So one of the keys to managing the hazard may be to identify the smallest earthquakes when they begin to occur, which is really the heads up that something larger may happen. And as we've seen both in Oklahoma and in Kansas, the ability to locate small earthquakes is very much controlled by the number of stations, which is less than adequate for the job in many of these areas.
That's a really good point, Bill, and that's part of the reason we're trying to get out into some of these surrounding counties and beginning to get some sort of baseline data before we see a lot of big disposal wells in those areas, so we'll have some sense of what's going on in terms of smaller earthquake activity.
This question is more for Rex and Austin. Is the information regularly being shared with the state emergency management agencies, earthquake program managers also?
Austin, I'll go ahead and then I'll let you answer that. From our perspective, I've talked to our emergency preparedness a couple of times on the state level. I think I can safely say the level of interest is much higher in Kansas on the local level than it is on the statewide level. And on the local level, particularly in Harper County, the county that's seen the most of this, we talk to those folks fairly regularly. In fact, I've got a conference call with their head of emergency management just this afternoon because, again, when you come from a relatively quiet state the way we do, we don't do earthquake drills. We don't, our building codes are still sort of taking all this stuff into account. So we're playing a little bit of a game of catch-up and trying to communicate between the folks on the science policy side and the emergency management side is real important. So that's a good question. And I can say in our world, the focus has really been on the local level, much less on the state level.
So here in Oklahoma, the greatest rates of seismicity began picking up in 2009 and really kicked up in 2010, just east of Oklahoma City, just outside the state capital. And so we've been interacting with the Oklahoma Office of Emergency Management since 2010. We've been creating educational information and keeping them informed. And of course, earthquakes were always on their radar, but still tornadoes are the greatest risk and challenge for their management system in the ice storms we experience. So they're clearly aware of the hazard and are preparing for it, educating the public and working with us. And so we've long had that cooperation with the Oklahoma Office of Emergency Management.
Austin, your point's a good one. I can tell you the folks, especially this time of year in this part of the world, worry as much or more about tornadoes than they do about earthquakes.
Rex, I've got a question here for you about the KCC. And do you know how the KCC determine the levels of volume reduction?
That's probably a better question for them than it is for me. I think they, in the course of making those decisions, I think they started off by looking at levels that were really what we would call levels that you would see in disposal wells in pre-earthquake days. That is, before we really started seeing a lot of horizontal drilling, a lot of the high volume wells might be 5,000 barrels a day. That was what wells did back in pre-earthquake days. So I think they started looking at that, but I think they also were trying to come up with levels that would allow the companies to adjust accordingly over time, and as a result came up with numbers that are somewhat higher than that. But exactly how they arrived at that step-by-step cutback is probably more of a question for them than it is for me.
Great, thanks. And then we've got one question here about, are the current seismic networks across the central and eastern United States capable of detecting the smaller predecessor earthquakes that you mentioned?
Unfortunately not. The seismic monitoring in the eastern part of the United States, up a little bit past the Mississippi River going west, have been improved significantly by at least the temporary addition of seismic stations on a grid pattern. And that's certainly going to help with general detection there. But our experience, particularly with special studies such as those that we've discussed here in Oklahoma and Kansas, suggests that we'd really like to be reliably locating, not only detecting, but precisely locating earthquakes down to about magnitude 1 or so. and that will require more stations than we have currently. Certainly, the OGS and the KGS are doing the best job they can with the resources that they have, and working together with the USGS, we're doing what we can to improve the monitoring, but we're not really where scientifically we would like to be.
I would like to add one thing to that. So the Oklahoma Geological Survey has operated a network since 1978. We've roughly been able to detect most magnitude 2 or larger earthquakes. And so we've been adding to our network consistently since 2010. And we have another 5 permanent stations or 6 permanent stations to distribute throughout the state. However, this won't get us much below this magnitude 2 sort of detection threshold statewide. There'll be areas where, of course, we can do much better than that. But what it does do is allow us to say a lot more about the magnitude 2 earthquakes we're locating. And to get down to that magnitude 1 range, it requires very dense instrumentation, and that's a big expense. And the state at this point is not able to take that monitoring effort on. But we've been doing a lot to enhance our monitoring and are well positioned to continue monitoring. However, we're having so many earthquakes that it's a real challenge just to keep up with the seismicity within the state.
Thanks. Another question is, it's about the seismic data. One of our participants is wondering, is that seismic data available in real time to the public?
Well, certainly all of the U.S. Geological Survey data is available in real time through our website, and much of the data from these other collaborating networks is as well. I'll let Austin answer about availability in Oklahoma, which I know is quite good as well.
Absolutely. We make a real point to make sure that all our data is publicly available and available to researchers. That's a big part of what we do, especially since our time is so limited. It's important to have researchers from around the country and around the world being able to use this data.
Yeah, and this is Rex, and I would actually say we're probably a little behind the curve on that, since we really just got the temporary stations that we put in installed over the last matter of weeks. In fact, we're getting ready to move one of them again. We will get to where Oklahoma and the USGS are, but we're not there yet. We're still sort of getting stable in terms of getting this network established.
We've just got time for one last question here today, and that would be, what's the basis for developing the trigger benchmarks that could lead to reduction or ceasing injection, and how involved are the various stakeholders such as seismologists, regulators, industry in that?
Austin, I'll go ahead and answer for Kansas. If you look at that action plan I put the URL up, you can see sort of the various components that went into that. That was a formula that was developed by folks at the Geological Survey, the KCC, and Kansas Department of Health and Environment. But we opened that up for comment from the public, and we got input from a variety of industry people, the general public as well. We went back and revised it somewhat, got another round of input from them. We then actually made an adjustment on the scoring in January because it wasn't always turning up exactly what we were after. That formula actually did not get triggered by the 4.9 earthquake just because it was a single event kind of off by itself. We knew sort of intuitively we really want a 4.9 earthquake to trigger looking for disposal wells. So we've gone back and tinkered with that formula and revised it in January.
The levels in Oklahoma are established by the Corporation Commission. Of course, I try to help explain the seismicity and what we can say about the seismicity and the uncertainties associated with what we know. And it's been an evolving sort of trigger level for the Corporation Commission, and they've changed how far out they buffer. They started like a 2-mile buffer and then a 3-mile buffer, and now we're at a 6-mile buffer. So it's sort of an evolving process as we move forward. And certainly the science helps inform this, and that's why it's important to get the peer-reviewed science out there and the science to help inform regulator actions and decisions.
Great, thank you. Well, that's all the time we have today for our question and answer session. If you have any questions that weren't addressed today, You can email them to us at cipinfo@americangeosciences.org, and we'll make sure to send your questions along to the speakers. So thank you again very much to Bill, Rex, and Austin for speaking today. And this concludes our webinar for today. Thank you, everyone.